Hello, welcome to developmental biology. Okay, looks like all the cool people are here. A lot of losers didn't come. That's okay. Today we've got a quiz. I suggest you go and do it. You've got, I think, 15 minutes to do it. I'll show you where it is. All you probably know already, and I'll give you a chance to do it. Four two. Is that today? That's today. There's your quiz, people. It's in progress. How long does it last? 17 people take it already. What the hell? All right. Okay. Don't wait for me. It's all right. Okay, so I just set it to close at 10 minutes after 1. So you've got until then. Okay, we're back. Let's take a look at this. Take a look at this. Now that it's closed, I believe. I'm wrong. I'm lying, I'm dying. What class is this anyway? Oh, I guess this is developmental. Okay. The dorsal ventral patterning of somites is induced by gradients of several factors. Dorsal ventral. The ectoderm and the dorsal neural tube. I've got a chat here. It's the word chat person. I'm not sure if it's closed. Oh, okay. Let's see. It should be. Says it should be closed at 10 after. It's now 11 after. Okay, people, let's see your faces real quick. Come on. Elijah. Angelique. Abdou Sabor. I just found out some interesting information about Abdou Sabor today. You've got a sister who's a freshman, don't you?
Yes, I do.
And you weren't going to tell me, were you?
I didn't think you wanted to know that.
I'm just busting you. I'm just busting you. We need to talk, by the way.
All right.
I'll send you a link. Okay, so is that thing closed? Is the quiz closed? This is yes. This is no. Who knows? Yes. Yes, the quiz is closed. All right, so let's go over the quiz real quick. All right. I hope I know the answers. I actually didn't. I wrote this a year ago, so maybe I don't even know what I'm talking about. Wouldn't be the first time. Okay. Dorsal ventral patterning of somites, dorsal ventral, is induced by gradients of several factors. The ectoderm and dorsal neural tube release, I believe it's Wnt. Somites, somebody's chatting me. I cannot see it. Damn it. I do this every time. New share. Okay. Somites in their area become dermomyotome, notochord, and floor plate. Know the central size. Know the central size? What the hell does that mean? Release Sonic Hedgehog, which induces the ceremotes to form sclerotome. The lateral mesoderm releases BMP, which then forms a lateral medial gradient to pattern the myotome. All right. Submit, finish. Let's see if that's right. I think that's right. No, it's not going to tell me. Fill in correct responses. Okay, good. I got them right. See, Kwame thinks I'm stupid, but I'm not. Okay, somite formation. Mesenchymal cells enter through the, I'm going to say node. I haven't even read this since last year, so I may get this wrong. And then move through the differentiating wavefront. In this area, they experience the hormone retinoic acid, which is inhibited by the hormone. No, I think I'm going to take this there. I'm going to say FGF here. I'm going to take this out. I'm going to put pre-Semitic here. It's chatting me. I do not think that. Kwame. Thank you, Kwame. I need that. Some lights begin to differentiate as they pass the differentiating wavefront, although they are already faded by the Hawkes genes. This is all what we talked about in the last class. And so might separate from each other due to notch signaling. I think I got that one right. Ta-da! Dr. Slish is smart. Okay, Xenopus. Xenopus, really? Oh, yeah, don't worry about this one. I'm not going to grade these. I'll give you all credit for that because I don't have time to go through and grade all these essays, but let's look at it anyway. Gastrulation I, whatever that is, Xenopus, in Xenopus involves changes in cell contact with other cells and the extracellular matrix. Explain what these connection points are and how they are regulated during Xenopus gastrulation. So this is chapter 7. We haven't really talked about this yet. Cell contact with other cells, I did say a little bit at one point. That's your cadherin junctions. And with the ECM is your focal adhesions, which are integrins. Yeah, and the rest of this question is making me sad. Okay. So that's that. All right, so I've got one more lecture to do to complete chapter 5, and then we have a test Monday. So I'm thinking, why don't we just review today? I think we've already done a whole ton of material, and I'll save that last lecture or two. It's really 2 lectures for next week. Today I'm just going to review. So I'm going to pull up the PowerPoint. Oops, that's not what I want. And just go through it. If you have any questions, please feel free to interrupt me as we go. Your Santa shows. Santa shows. We are Santas. Okay. So starting out with Chick, reviewing. This is just a review of chapter 3. Just remembering that we've got, by the time we start, we're going to have this hypoblast covering the yolk, and we'll have Kohler sickle at one side, and the epiblast, which is the actual embryo proper, is on top, and that's subgeminal space. Now, Kohler sickle is because of the rotation of the egg as it goes through the oviduct, and it's rotating in this direction while the shell's being put on. And whatever is at the top will be posterior, and that's where Kohler sickle is going to be. And then the anterior end is the other side. Okay, so over here at Kohler sickle is going to be releasing VEG1 and Wnt. VEG1 is the TGF beta-like signaling thing, and it goes to SMAD2. I just looked that up. And Wnt is Wnt. So you've got nodals and Wnt coming up, and you've got your hypoblast all across here, and that FGF and Wnt are going to induce these epiblast cells to start releasing nodals, and that nodal release is going to be blocked from going in this direction because the hypoblast is releasing Cerberus. So that's blocking the spread of that and stopping the start of the primitive streak movement to the anterior side. Prospective endoblast here is going to change that. This is going to grow over this way and displace the hypoblast. So here you can see I kind of BS this down here. This is hypoblast here in green. It's being pushed this way, displaced by the endoblast. So this blocking agent is being displaced at the same time. Oops. So here, Kohler sickle is now releasing FGF, and the FGF and the nodals together are causing the epiblast cells to divide, converge, and then go through and start forming that primitive streak with the cells coming through and in and forming 3 layers of cells there. FGF here, we talked about later in terms of neural induction. We also said at the later, we say FGF turns ectoderm into neuroectoderm. At this point, the ectoderm is not competent to respond to FGF in that way because the chromatin is all bound up. And we'll talk about that later when we get there, but keep that in mind. FGF is a neural inducer, but not right now. Right now, what we're getting is mesenchymal cells, which are mesoderm and endoderm, mesendoderm, and they're coming through that primitive streak and they're crawling anterior and lateral, and they're going to make layers of cells here. So up here, we're looking at it from the side, like we're looking from the left side through to the right side. Here, we're looking at it sectionally, kind of like from the posterior towards the anterior end. And we've got cells coming through the primitive streak, crawling underneath, and the primitive streak is expanding in the anterior direction. Once it goes as anterior as it's going to go, Henson's node forms, and cells are still coming in through that node at this point and going anterior and lateral. And those cells are these bad boys here. These are going, here's the node, they're going forward, and lateral. And what that's going to do is this, okay? So your node is back here, these cells came forward, and so these mesodermal cells are underlying the ectodermal cells here. And you can see this is yolk right here. So this is happening in that subgerminal space. So these cells come forward and then they start releasing FGF. And that's going to, and now at this point, these ectodermal cells are competent to respond to that FGF because this is way back at the beginning of the primitive streak. All the FGF responsive genes are tied up with histones. At this point, they've been freed up. So now when this releases FGF, this becomes neural. And neural is going to be like a thickening, and then that becomes the brain. Okay. And then we start to regress. And as we regress, here is your node. And then now we've got this FGF gradient that's going to be causing cells to divide and also to become mesenchymal. So, okay. So now we're here. Cells are here, they're going forward. They're going to make this head process up here, the head fold and all. And now your node's going backwards. And that's neurulation. So this is that whole area where neurulation is happening from Henson's node to this formation of somites. Now I'm going to save discussion of this until later. We're going to bring mouse up to the level of neurulation, and then we'll talk about neurulation in general because the same thing applies to both. Although we talk about it in terms of chicken because it's just easier to see. I'm not going to talk about the signaling pathways, although they are important. If I have time left, I will. I don't have a lot of time today, as opposed to most days. Okay, mouse development, early mouse development. You have an embryo, a zygote, that divides 3 times. You end up with 8 cells. And eventually we end up with this structure here, this blastocyst, where you got the blastocele and inner mast cells. How do we get from here to there? Thank you for asking, because that's what I wanted to talk about. So here we are at the 8-cell stage. You've got inside cells and outside cells, and they compact, that compaction thing of the morula. And before they compact, all the cells are expressing both CDX2 and OCT4. And remember, CDX2 inhibits OCT4, OCT4 inhibits CDX2. They're both being expressed at a low level. So as soon as something happens to make one go up, the other is going to go down. These are transcription factors, keep in mind. Okay, so when you get to the 16 to 32 cell stage, you end up with inside cells and outside cells. And the inside cells are all OCT4, and the outside cells are all CDX2. And why is that? Because of our old friend Hippo. The Hippo signaling pathway gets active when the cell is touching something all over itself. So down here in the inside cells, they've got active Hippo, and Hippo is going to break down a transcription factor, YAP, that causes CDX2 to be made. So then that represses CDX2, OCT4 comes up, further repressing CDX2, and before you know it, lo and behold, all you've got is OCT4 being expressed. On the outside cells, Hippo is inactive, so YAP binds to TEAD4, and that increases transcription of CDX2, which inhibits OCT4, and you get only CDX2. So here's our Hippo pathway. Here's the summary. Inside cells are activating Hippo. Hippo's blocking YAP. So OCT4 blocks CDX2, and now you've got only OCT4. Outside cells, Hippo's not active. YAP and TAD4 get together. CDX2 comes up and inhibits OCT4. And those outside cells then become trophectoderm, which will be extra embryonic. Okay, blah, 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 blah. Now we have to change those internal cells. So at this point, you've got OCT4 all over these inner mass cells here. And they're both going to, and all these inner mass cells will then start to express NANOG and GATA6. And then they will, or actually some have got NANOG and some have got GATA6. And they will rearrange themselves. So the GATA6s are on the outside and then NANOGs are on the inside. The outside cells then will become primitive endoderm. And this is the embryo proper, the nanog. Okay, so that nanog expressing cells become the epiblast, and this is the primitive endoderm. Now, the proximal side of this blastocele, blastula, will implant in the uterus, and we'll get this extra placenta, this cone of tissue over here. Ectoplacental cone forms. So your placenta forms there. And then we've got extra embryonic endoderm. And this starts to proliferate, and that forces the epiblast down and into this cup shape. This ridiculous cup shape. And that primitive endoderm then becomes visceral endoderm, covering the whole outside. And then we still have, don't forget, trophectoderm all around this, which is, you know, the big trophectoderm thing. So we've cut that away in this picture. So we've got your cup shape now with epiblast here, surrounded by visceral endoderm. Let's go forward a bit. And now we're going to talk about how we get to the primitive streak state here. The epiblast will release nodals, which will convert some of the most distal part of the visceral endoderm, the distal vesical endoderm, DVE, into this DVE. The DVE then releases lefty and other blockers of nodal, Wnt, and BMP. And because of the influence of nodals being released here, that will start to go towards one side. And when it does, it's called the AVE, anterior visceral endoderm. And that will keep the underlying epiblast anterior here by basically blocking everything. All the hormones being released from here on out are going to make things into mesoderm and make them crawl towards the dorsal side. Or, yeah, the dorsal side. So blocking everything here, we're keeping this anterior, so all the action is going to happen at the other end. Okay, so this is going to be anterior. You've got this proximal region of the epiblast here that's going to get signals from the EXE, the extra embryonic ectoderm. So this is releasing nodals, and nodals are causing Wnt to be produced, and Wnt is causing nodals to be produced, and BMP4 is causing Wnt and nodals to be produced, which are causing BMP4 to be produced. It's this big self-congratulatory hormonal release. Everyone loves everyone. Okay, so your EXE is releasing nodal, BMP4, and Wnt. And each of these is causing the production of Wnt is causing nodal, BMP4 is causing Wnt, nodal is causing BMP4. So they're kind of sustaining themselves with their production. And these are going to cause brachyury to come up in that proximal or the proximal epidermal rim. And also you've got visceral endoderm producing Wnt, which is causing this to produce Wnt to release on this. So this is another back and forth kind of a thing. That's what I was showing, oops, here. Visceral endoderm making Wnt, and then the epiblast making Wnt in response. So that's what's going on here. So you've got all this love fest of hormones going on here, making everything mesodermal except where the AVE is, because the AVE is blocking all three of these by releasing lefty, Cerberus, and Dickoff. So these then are causing these cells of the proximal rim to turn into mesoderm and mesenchymal. So they're starting to move, and they can't move this way because they're blocked. So they're moving this way, and this is what starts that primitive streak. So cells will come over here and go out of the embryo and then around and cover the outside of it. Remember, we're inside out here. So it's the same direction as chick, except it looks different. So it looks kind of like they're coming from the inside out, but this is going to be the ventral side, the dorsal side's on this side. So it's really going from the out to the in. I know, it's confusing. Okay, so that's what causes the primitive streak to happen here. Those hormones are coming together and they're causing this mesenchymal movement out, and then that node would move from here, which is posterior, up towards the anterior pole over here. Okay, here it is here. So the organizer gets this far, and you still have cells coming out through that node and going anterior and lateral, and they're going underneath this ectoderm here, and that's where your brain is going to form. And so your head and brain are here, and now this node is going to reverse and go that way, and your spinal cord will be there. So when that node reverses, that's neurulation. Any questions? I'm going over this fast, I know. Hopefully it's going to be, you've studied already. Hopefully this isn't the first time this isn't the second time you're hearing this, and it's going to jog your memory here. But anyway, that is your mouse up to primitive streak. Okay, so now neurulation. So before neurulation even starts, as I just said, you've got cells coming in through Henson's node and going forward and anterior. And that's what this is, going lateral and anterior, and that's going under that ectoderm. And that ectoderm now, that ectoderm now is going to be made into brain, right? That's now we've got, as I was alluding to earlier, the FGF is now a neural inducer here. So that mesoderm is releasing FGF, and we're converting this epidermal ectoderm into neural ectoderm, and that's where your brain's going to form. And that's ahead of the node. So the node's now going to go in this direction. And this is where we set up this whole somite formation, the somitogenesis. So here's your node. Let's look at it closer. Here in the node, you've got this stem zone. And the stem zone is wicked full of FGF and Wnt, right? FGF is causing Wnt production, and the cells are releasing FGF. So you've got a ton of FGF and Wnt being produced here. And that makes these cells neuromesendermal. So as they are being produced in this self-renewing stem zone, the cells come out as kind of somewhere between neural and mesenderm. And then as they migrate away from that spot, they start to differentiate into either neural or mesendermal cells. And that has to do with the transcription factors that they're upregulating. The neural cells will then express SOX2, and they will become the spinal cord. Mesendermal cells then express brachyury, and that's why they're mesenderm, and they become somites. So here we are, our neural cells coming out this way, gathering in the center, forming neural plate. And then this is nodal cord underneath it, which will induce that neural plate to become neural tube. And then you've got these mesendermal cells coming around the outside, diving in through again. Still, these are all diving in through. And these then will become somites when they hit this differentiation wave front. Ooh, remember that? That's pretty cool. So anything in this area is called presemitic mesoderm. So these are cells that are mesodermal, they're mesenchymal, they're dividing, and they're moving. Okay, okay, yeah, let's just leave it at that. Okay, so what happens then, the gradient of FGF then is what's going to make this determination wavefront. And just to go back real quick to remember how this works. At the front of the node, you've got cells that are dividing and producing FGF. So FGF is really high at the front end of the node. And as the node moves away from those mesenchymal cells, they start to experience less and less FGF. So the FGF is decreasing as as these cells get away from the node. Also, you've got a gradient of retinoic acid coming from the somites in this direction. And FGF is going to inhibit the production of retinoic acid by inhibiting the production of the enzyme that makes it, and by upregulating the enzyme that breaks it down. So FGF is inhibiting retinoic acid. Retinoic acid is going to inhibit the production of Wnt and FGF. So as the cells are moving through this, they're going to be seeing FGF until you get to a point where there isn't enough FGF to inhibit retinoic acid. So then retinoic acid is going to take over and shut off FGF. So that gives us this kind of distinct threshold of FGF concentration, because you've got two overlapping gradients that inhibit each other, and so you get a really sharp demarcation. And that sharp demarcation then is our differentiation wavefront. Right here, or the determination wavefront. And after the determination wavefront, those mesenchymal cells go through mesenchymal to epithelial transition, which means they stop moving and they become a somite. So your node is here, it's moving in this direction. Cells are being produced here, and they're moving backwards, and they're seeing less and less FGF. And then suddenly FGF shuts off, and boom, they stop moving, and they become a somite. Internet connection's unstable. Hang on a sec. Okay. What else do I want to say about this? Okay, so the next step is, how many somites do we end up with? So if you look at different species, you look at a giraffe versus a mouse, you've got a lot more vertebrae in a giraffe than you do in a mouse. And that giraffe is lousy thick with cervical vertebrae, as opposed to the mouse, which has got a short neck. So why is it in some animals we get a lot of vertebrae and in some we get few? It has to do with the clock and wavefront model. Clock and wavefront model. So the idea is, as these mesenchymal cells are moving in this direction, you've got these two feedback mechanisms between FGF, Wnt, and Notch that are constantly cycling. FGF causes Wnt production causes Notch production, and Wnt and Notch then shut themselves off. And so now, Wnt, Notch, and Ephrin A4 go up, and then they come down, and then they go up, and they come down. So every 90 minutes, you get a peak of Ephrin A4, and then it goes away. Peak goes away every 90 minutes. And once the cell gets past this determination wavefront, there's no more FGF to keep that cycle going. And so, boom, we stop at this point. Now we've got Ephrin A4. That causes differentiation into a somite, and it causes that mesenchymal to epithelial transition, MET. Okay? So the idea is, if that thing is cycling fast, then you're going to have like a low beat going past that determination front a lot more often and get more vertebrae than if you're cycling slow, and then you've got less frequent passing of the determination wavefront and you get fewer vertebrae. And that's too, when you get into Evo Devo, which I'm hoping to do a little bit of this semester, although I'm not an expert at it. That's how you can get the difference between a chick that has 43 vertebrae and a snake that has 250, right? The speed of that clock going as that node's going at a constant rate. Does that make sense? Let's hope so, because nobody's saying nothing. Okay, so that's part of the story, why we get the number of somites we get. But the other part of the story is why somite 1 is different from somite 2, which is different from somite 3. In other words, AP patterning of the somites as they come down. And we saw through this really cute experiment, if you take pre-mesenderm, that pre-Semitic mesenderm from a late stage embryo, and you put it further up in a younger embryo, it's still late stage somites, right? It's still giving us what should be thoracic, but now they're up earlier because you stuck them up earlier, which tells you that those cells, when they are in the in that pre-Semitic mesenderm state, are already patterned. What the hell is patterned? Oh, Hox genes. Hox genes, of course. Genes. Sorry, that was pretty gross. Hox genes. So you've got 4 different clusters of Hox genes, A, B, and C, and each one has got up to 13 different genes within it. Some of them are missing from here and there. So these will be activated sequentially. The number 1s get activated first, and the 2s, and the 3s, and the 4s, all the way down to the 13. And you can kind of think, as the node starts, the first ones are being activated. As the node hits the, as the node hits the posterior, oh, what am I doing? As the node hits the posterior end of the embryo, the last ones are being activated. And so this is the anterior end. The first few Hox genes get turned on. They never go off. As the node advances, different ones get turned on, different ones, different ones, different ones. And by the end, they're all on. And this is because of this sequential way they're regulated. Wnt signals turn on the first ones, and the first ones turn on the next ones, and they turn on the next ones, the next ones, till you get to the very last one, and the last one blocks the earlier ones and shuts the whole system off. So those Hox genes are going to be turned on during neurulation, and they turn on in a wave like this. So the node is moving backwards, and a wave of Hox gene activation comes in this direction. So as as the mesenchymal cells go through that presemitic area, whichever Hox genes are on, stay on when they become somites. And so those somites, each of them will have a different combination of Hox genes turned on, and that tells them where they are within the AP axis of the embryo. And different combinations of Hox genes will give you different AP areas of your body, right? And the same combination of Hox genes will give you the same spot in all your different phylogenetically related organisms. So here we are with the chick. Hox gene C5 comes in at the end of the cervical. Here in the mouse, at the end of the cervical, C5, right? You get into thoracic. The chick doesn't have many thoracic, but you've got the same Hox genes turned on in thoracic there as in the mouse. So that combination of Hox genes tells you where you are in that AP axis of the body. And there, again, just to repeat, because I like this slide, they get turned on in a wave that goes from posterior to anterior. And whichever Hox genes are turned on as the node goes past and makes somites, those are the Hox genes that will stay on in those somites. And so they've got their regional specification based on that wave of Hox activation. It's beautiful. It's absolutely beautiful. Okay, so now that they know where they are AP wise, how do they know where they are dorsal ventral wise? Because that's going to make a difference too. So this is kind of like after they become somites, now they're going to be induced to become what they need to be in that area. So one thing is this isn't that important. I haven't seen it come up again in the textbook, so we're not going to worry about it. This is more important. So you made this somite, which before you get any induction happening, these cells just went through that mesenchymal epithelial transition, and they're all just generic somite, so generic mesoderm. Now they're going to turn into specific mesodermal tissues. How does that happen? Well, this is all just kind of paraaxial, right, next to the axial. The axial is the very center, and this is the neural tube, and here's your nodal cord. So your neural tube and your nodal cord and the lateral mesoderm are all releasing hormones at this point. So you've got 3 different gradients of hormones going on. You've got sonic hedgehog coming from the bottom of the ventral side of the neural tube and from the nodal cord. So you've got high sonic hedgehog here, low up here. You've got Wnt coming from the dorsal side of the neural tube and from the ectoderm. So you've got high Wnt here, low Wnt here. And then you've got BMP4 coming from the lateral side towards the center. So you've got high BMP, low BMP. Those are your gradients. And those gradients then are going to cause the cells of the somite to differentiate into different tissues based on what concentration of each of these hormones any particular cell is experiencing. So what do they become? I'm glad you asked. First of all, the bottom of that somite will become sclerotome, and sclerotome will become muscle, and these cells will undergo epithelial to mesenchymal transition. So they start to move again, and they will surround the neural tube and become vertebrae. The rest of the somite is dermomyotome, so it's both skin and muscle. That will then differentiate into myotome. We've got medial and lateral myotome, and then dermotome. So dermotome becomes the dermis, And I'd just like to point out, dermis is the mesodermal part of the skin. You also have ectodermal part of the skin, which is the epidermis. So this is going to become this dermis area. And the lateral myotome will become abdominal muscles. Abdominal muscle. Body wall. Okay, it's going around your body this way, from my body, from the back to the front, like this. So covering up. Time is it? 1:50. Class is technically over. So I would seriously suggest, if you're not following this dermal myotome and myotome bit, watch this again. This guy does a really good job of it. He gets a little more depth than what we need, but I think I like his pictures better than the ones from the book. Okay, and that is that. I'm not going to get into. You need to know the signal transduction pathways, but I'm not going to talk about them right now because I'm out of time already. If you're looking at my PowerPoint and you get this far, you've gone too far. I'm going to talk about these neural crest cells, next Wednesday after the exam. So anybody left? Oh, some people are still here. Any questions? God bless me. May the beer gods bless me. Any other questions, comments? So the exam, so what we did today, Tyler, is not the exam. Oh, he's not on the exam. Oh, thank you, Tyler. No, I'm just talking, Nothing we did today is on the exam. We're just talking here. Are you kidding? This is the exam. Will there be a practice exam posted? Is there one in there now? Let's take a quick look. There may be one there from last year. If not, I really don't have time, unfortunately. Editing quiz. Okay. I think last year I wrote one up and I gave the answers too. Exam 3. Practice quiz. Oh, practice quiz. Here's the exam. I might as well. No, I can't. I'll show it. What the hell? Although it's not ready. You can't see it. That's about it. I can open up these practice things, I think. So you could play with those, but I don't have a practice exam, unfortunately. The exam will be like the last exams, where it's some objective drag and drop kind of stuff, and then some essay questions as well. Get out of here. Yeah. So, anything else? Vanessa going back to sleep? Good for you. Good for you. Time is it? 10 to 2? Maybe I'll take a nap too. Okay, no questions. I'm going to call it a day. See you, Yusuf. Bye, Vanessa.